proof, which is quite long. And okay, so Andek, we're looking at simple kinetic models of gases, question 4 to begin with. Now you'll have to remind me of the formula. So question 4, what did we say the formula was for the energy? Is it 3 over 2 PV, was it? So is my answer wrong, you think? Okay. Right. Well, we know what the volume is because the volume is a ball. It's this one. The volume is a ball, so it's going to be 4 over 3 pi or cubed, yeah. But what's the pressure? So we have a balloon, and we know the radius is actually 30 centimeters. Yes, question. Yeah, no, that's the page. Number 4. What's the pressure? Who can tell me what the pressure is? Oh, it's not anywhere. You need to know it. Any ideas? What if I said the pressure is 1 atmosphere? Yeah. No, why? Well, think about it. If the pressure was less than 1 atmosphere, then the balloon would be being squeezed by the air around it. And if the pressure was more than 1 atmosphere, it would want to expand. The pressure on the inside and the outside, they have to be equal for the balloon, you know. You ever see those hot air balloons? The ones that go really, really high, the silver ones? When they move up in the atmosphere, they actually expand. And the reason they expand is because the pressure needs to reduce. Because the pressure has to match the outside pressure. And we know as we move up, the pressure goes down. So it's actually 1 atmosphere here. What was it, see, about 101,325? 325. And the radius is 30 centimeters. So if you hit that in for me, Matt, what do we get?
The radius is 30 cm.
Oh, sorry, thank you, it's 15. The diameter is 30. Right, what do we get here? Two one four eight point seven. Is it 325 or 324? Anyways, it doesn't matter because if we do 3 significant figures, it'll be 215. Yeah? 00 joules. 2059. Okay, yeah, read it to me. Pretend I'm stupid. Read it to me slowly.
2150
Joule. No kilo.
No.
Oh. Oh, so my answer seems too big here. Are you sure? This seems very small because we have 101325 in it. Yeah. Okay.
Yeah.
There's not an extra 0? Okay, I believe you. Right, so 215, so the answer needs to be fixed then.
How can I know 0 point?
Yeah, in the question I said it's 30 centimeters wide. So I said it's 30 from here to here in the question.
Wow.
So the ore is 15 centimeters. Half it.
V is.
Oh, this is the formula for volume. Volume of a ball. Yeah? Is that okay, Matt? Yeah. What are we doing next? Okay. Now, do you think my answer is wrong again? Badly wrong. I might have been quite hungry when I did the answers.
Yes.
Yes, what? I'm badly wrong? Or a little wrong? Badly wrong, okay. That's better than being a little wrong. That's being wrong in style. Okay, 5. A gas cylinder with radius 3 centimeters and length 10 centimeters. A mechanical arm pushes down on the cylinder and reduces its length to 5 centimeters by applying a pressure of 2 atmospheres. How much work was done? Right, so we said the formula for work here is pressure times the change in the volume, which will be 2 times 101,325 times pi times r squared times the height. Right, so what's that, please? That is okay. We all make mistakes. What's the answer? Wonderful. Wonderful. That's my father. He's very cheap. He likes to call and hang up, so I call him back. You probably have friends like this, right?
Yeah.
Yeah, yeah. Okay, do we have this one? Yeah. Okay, so the second part is what's the force. So who knows what formula I could use to get the force? Now, I'll give you a little hint. You've just worked out the work. So what would be a useful formula to use?
Work equals to force times distance.
Yeah. So therefore, force equals work over distance, which is 28.65 over 0.05. I'm hoping that's 573 newtons. I better send them a text message. Okay. Is that okay now for you, Matt? Right, what are we having a look at now? Kim, you look like you have a question. Which one do you want to see? Sure, 2.
So
Yeah.
the work equals to pressure times change of volume.
Yes.
I've never seen that before.
What? Didn't we do this one in class? I thought we did. It was right after we did the proof for P.
Oh,
Yeah. See, you know, it's not that you've never seen it before. It's just you forgot you've seen it before. All right. Will we have a look at number 2 now? Yep. Okay. So On the same page, number 2. Teachers flying when the pilot reports the plane is 10,000 feet high. So this here is 10,000 feet. And I tell you that roughly 3 feet is about 1 meter. Roughly. So this is roughly 3,333 meters. Now it's not exactly, roughly. And also the teacher assumes that the air, its density is roughly, now again it's not exact, roughly 1 kilogram per meter cubed. What's my question? What's the pressure? What's the pressure? Okay. So we have this formula for pressure, don't we? It's pressure equals rho g h. Yeah. Although there's a small problem, we don't know the h. Because you might think the h is this, but it's not. Where do we measure the h? We don't measure it from the ground. We measure it from the top. So this is the h here that we have to use. Yeah? Is that okay? Or you like, huh? Because this formula, it's the pressure for how deep you are. So you're always measuring downwards. Yeah. Alright, so we have a little bit of a problem. But there's a couple of things that we know, okay? We know what the pressure is down here. What's the pressure at the ground? 1 atmosphere. So we can say 101,325 pressure equals rho g, and that height is h plus 3,333. Because you're looking at this and this. Okay? Now let's make a second equation. Now let's imagine we're here. What's the pressure? We don't know. That's what we want to know. That's equal to 1 g h. In this case it's h. How many equations do we have? 2. And how many unknowns? 2. So we could work out both the p and the h. Although I don't really care about the h, do I? I care about the p. So what I could do is I could say h is p over 9.81, and I can put that into this formula. So now I get 101,325 equals 9.81 p over 9.81 plus 3,333. Now I can solve. Okay. Now, remember, the teacher is doing this question in their head. Okay? So, if you were really on the plane doing this, you would make all the numbers convenient, So, you wouldn't say 101,325. What would you probably round it off to? Maybe you would say it's 100,000. And 9.81? You would round it to 10, wouldn't you? And p over 10. And maybe you'll say 3,333, or maybe you'll say 3,000. We'll go with 3,000. Okay? So, Japers, how many zeros have I got here? 1, 2, 3, 4, 5, is it? So 5 zeros equals p plus, how many zeros here? 3 multiplied by 10 is 4. So you see, it's easy to do this. That's 100,000 minus 30,000, that's 70,000. So you could say that the pressure is roughly 0.7 of an atmosphere. That's the reduced pressure in the plane, in the sky. Okay? That's, what did I say in the question? Oh, I said it's, 69,000 pascals. Yeah, so it's about 0.7 of an atmosphere. Now, when you're inside the plane, it's not like the example with the balloon. Do you remember I said with the balloon, the pressure on the inside and the outside has to match? Yeah. It's not quite the same with the plane, because when you're up at 10,000 feet, the pressure isn't really 0.7 inside the cabin. So the plane has to be very carefully made so that it can hold its shape under the higher pressure. Because what the plane wants to do is explode. Because the pressure inside the plane is bigger than the pressure outside the plane. So the plane is wanting to expand, okay? But it's being held together by the steel, yeah? This is why if the window breaks, or anything in the plane breaks, then the plane has an opportunity to expand and let the pressure inside reduce to match the outside. So this is why when you see in movies, when the door opens, everything starts moving out, because the pressure is being reduced, because everything is escaping. The volume is trying to expand. So the air inside expands and just rushes out, you know?
If it drops, then the air coming in.
Say again?
If it drops, then the air coming in.
If the pressure drops,
I mean, the plane drops, and the air will go in.
if the plane drops, no, because it would have to drop to below sea level, but then you're dead because it's below sea level. So, yeah, but I suppose so. If your plane dived into a valley and you open the door, then maybe the air would rush in. I don't know. I haven't tried that. Yeah. Yeah. That's an interesting one. The planes have to be very carefully made, okay? There has been some times when the window, well, okay, not sometimes, it happened once where the window for the pilot has broken off. The window just exploded out because it wasn't properly secured back onto the cockpit. You know, the screws were not fully tightened. They were only 0.5 millimeter too short, and this was enough so that it could, the pressure could kind of get out a little bit and then just explode out. You know, so the planes are very amazing engineering accomplishments, being able to, you know, keep its shape under the pressure difference, because it's quite a big pressure difference, you know. So planes are very, very well designed, very well engineered, very, very impressive accomplishment. Okay, right. What are we having a look at next now?
Thermodynamics.
Okay.
5.
Number 5. Yeah. So it's a bit. I don't know if the calculation one. Let's see. Water at a temperature of 10 Celsius and mass 500 grams is in a kettle on the stove. The stove is turned on and 100 kilojoules of energy is added to the kettle. What is the change in internal energy of the kettle? Alright, so you put 100 kilojoules of energy into the kettle now has an extra 100 kilojoules of energy. So the internal energy has increased by 100 kilojoules, that's fine. Now assume another 100 kilojoules of heat is added to the kettle, but now the kettle whistles and shakes. Will the change in internal energy be the same? Will it be 100 extra kilojoules inside the kettle now? Well, no, because some of the energy, yes, it became internal energy and the kettle became hotter, but some of the energy became work. the cattle started to shake. So not all the 100 went into the cattle as internal energy. Some of it was converted into movement. So the answer for part B is no. You don't look happy with this, Siva. In fact, you look very unhappy with it. Are you sure it's okay? You got my idea? I can trust you?
Yeah.
Okay. C. The heat is turned off, but the cattle continues to shake. What is happening to the internal energy? Alright, so you turn the heat off, but the cattle is still sitting there going, shaking. What's happening to the internal energy? Is it changing, staying the same, getting bigger, getting smaller? What's it doing? Yeah, why?
Spread out. The energy.
Yes, okay. But I was more thinking you would say the internal energy is getting smaller because if the cattle is still shaking, it's still doing work. And that work has to come from somewhere. And if you turn the heat source off, then it has to be taking it from the internal energy. Now, okay, also true, Matt, the heat is dissipating as well. But my little story was about shaking cattle, so that's what I wanted you to imagine. Is that okay, Siva? Yeah. And lastly, the kettle falls off the stove. What is the change in internal energy? That is, will it become hotter or colder? So the kettle is falling and it hits the ground. Now, just pretend the water stays in the kettle, that it doesn't spill out. Okay, so what happens to the internal energy? What happens to the heat? Is there more or less when the kettle hits the ground? Oh, now you're thinking now. You've got a 50-50 chance. Or maybe I'm tricking you. Maybe it stays the same. More or less are the same. Go on, Siva. No, go on. What do you want to say?
It should be colder.
Why should it be colder? Like, what's the logic? Yeah, it's closed. Pretend it's closed and it's, you know, wrapped up nice and it's in a kettle cozy. So I want to know what's the effect of it hitting the ground. What effect will hitting the ground have on the heat, the internal energy? Increase. Yes. But why? Make it more technical, more physics. No. Not good enough. Something else. So look, when the kettle was here, it has potential energy. Okay. When it's fallen and it hits the ground, it has kinetic energy. But when it hits the ground and stops moving, it neither has potential because it's on the ground, nor does it have kinetic because it's on the ground. So where did this energy go? It only could have gone into heat. In fact, the kettle will be warmer when it hits the ground. Now, you might not believe this, but it's true. And you can actually see this at waterfalls. You know a waterfall? Yeah? The temperature at the top is less than the temperature at the bottom because the potential energy became kinetic and the kinetic became heat. And actually, it was Joule. Remember we were talking about Joule and his experiment? He also did an experiment with waterfalls where he went to the top with a thermometer, measured the temperature, went to the bottom, measured the temperature, and he discovered the temperature at the bottom is greater than the temperature at the top. And the amount it's greater by is the correct amount for the potential energy to be converted into heat. Okay, so it will be warmer.
But not by a lot.
No, you're talking about like
with waterfalls.
Yeah, like 100-meter waterfall would make about maybe 1 Celsius. And that's 100 meters, you know, so. But that's enough to measure with a thermometer. You know, even an old-fashioned thermometer from 100 years ago, you could still, a mercury thermometer, you could easily measure 1 degree difference. No problem. Yeah. Is that okay, Siva? Yeah? Matt? Yeah, okay. What's next now? Which one, sorry? Which question? Yeah. 6 was an exam question a while ago, so let's have a look at it. Latent heat number 6 now. Oh, I'm so hungry. I'm wondering if I'm chicken shawarma hungry. Okay. What temperature does water boil at? 100. Now, liquid nitrogen is fascinating because it boils at minus 195. Minus 195. So, you have a little bit of liquid nitrogen and you pour it on your hand, and the heat from your hand causes the liquid nitrogen to boil because it boils at only minus 195. So, very quickly it becomes hot enough and then steam comes out. Okay, so that's the cool thing about liquid nitrogen. You can just pour it and it starts to boil and the steam comes up off of anything, you know. So the heat capacity of glass is 840 joules per kilogram per Kelvin. Now liquid nitrogen is at its boiling temperature. Now, just because it's at its boiling temperature doesn't mean it's becoming steam. You remember, water can be at 100 Celsius but still be liquid. It'll only become steam if what happens? What do you need to, yeah? Yeah, but and how do you do that? By giving it heat energy, okay? So, you see in the picture, the liquid nitrogen is at the boiling temperature, but it's not steam, it's liquid, because it needs a bit more energy to become steam, okay? So, we draw the picture, we have our glass. How big is our glass? It's 50 grams. And its heat capacity is 840 joules per kilogram per Kelvin. And the temperature is at 20 Celsius. And you pour in some liquid nitrogen and it comes out as a gas. And its latent heat is this. So just think about what's happening, okay? You pour in some liquid. How much? We don't know. So we'll just say it's M. And then what will happen to the glass? Will it become hotter or colder? Colder, yeah, because what's its temperature now? 20. So this glass will very quickly become colder. And what will happen to the liquid nitrogen? It'll become hotter. In fact, it becomes so hot, it boils. And this is the latent heat we require. So what we can say is the heat gained by the nitrogen is equal to the heat lost by the glass. Now, what temperature will the glass drop down to? Well, you keep pouring the liquid nitrogen until you stop getting the steam, which means that the glass has become the same temperature as the liquid nitrogen and it's no longer giving any energy to this liquid nitrogen because it's in thermal equilibrium. So the glass will cool down to minus 195.79, and at that point you can keep pouring liquid nitrogen, but the glass is so cold it no longer makes the steam. You know, it's a bit like, imagine you had very hot rocks and you pour water on the hot rocks, then you get steam. But if you keep pouring water, eventually the rocks cool down and you can no longer make the steam. It's the same idea here. Okay? So the gain by the nitrogen equals the loss by the glass. So we have M L, this is for the nitrogen, equals M for the glass, C delta theta. So M times 25700 equals 0.05 times 840, and the delta theta would be 215.79. because it went from 20 to minus 195. Is that right? Yeah. So, can you hit this in, please, Kim? Have you got your calculator? 0.3526. That's how much nitrogen you need. Is it okay?
I actually think I can compare two things.
This part. Yeah. Mhm. Bad news for you is that was a section A question, so it meant you had to do it.
Liquid nitrogen stay the same temperature.
Yeah, like usually the liquid nitrogen is poured out of like an insulated container, so it's kept at this temperature. Okay. What are we having a look at next? I'm sure there's a time. Yeah, there is. So what's next?
So it might be simple, but it's question 2, page 63, specific heat capacity.
Yep.
Just got confused with the math.
Which question?
Question
What page is this? Specific.
663.
Oh yeah. Which one did you say? 2. 2. Right. Two. Specific heat capacity. Whiskey, which is half alcohol, half water, roughly, of 50 grams is at 10 Celsius, is mixed with 500 grams of water at 100 Celsius. What's the final temperature? Okay, so this is what you have. Look, you have some whiskey. You have 50 grams of whiskey, which I said is like 25 grams of alcohol and 25 grams of water. And its temperature is 10 Celsius and 10 Celsius. And you mix this with 500 grams of water, as alcohol, water, water, at 100 Celsius. You mix it all together and you want the final temperature. So, will this gain or lose energy? The alcohol. And this one? Gain, and this one? Lose. So this one will increase to X, and decrease to X. These two gains should equal this loss. So, M C delta theta should equal M C, what's the, oh, it's the same, X minus 10, and what is the specific heat capacity of alcohol, please?
I'll get you.
2,300. X minus 10. So this can be, what's that? 2, 9, 5.5.
Yes. No, 2090.5.
Times 100 minus x. Now look, these two, this is common, so I want to actually take it out. So, can somebody actually do 0.025 times 4181 plus 0, the 0.025 is common as well. So I can take out 0.025 and then 4181 plus 2300, what's that? It's 4481? No, 6481. 6481. Okay, so what we'll do is we'll take these two under this. So somebody put that fraction in, please. Times 100 minus x equals x minus 10. So that's 1290 minus 12.9x equals x minus 10. So that means you'll get 13.9x equals 1280. So x is 1280 over 13.9. 92.1. My answer's off a little bit. I said 93.5. Anyways, there could have been a rounding error anywhere. Yeah, that's supposed to be like a small o for Celsius, so I screwed the typing up there. It's okay. You're writing that down? Okay. Did you write this down? Or did you already get this, Ken? Yeah. I mean, you don't need to write it down. You have it okay? Are you thinking about doing the aeronautical engineering? That's you, isn't it? Yeah. Where were you thinking of doing this? Like UK or Ireland?
Outside.
Huh?
Outside of Ireland or UK.
Oh, okay, not UK or Ireland then. Yeah. So is the aeronautical engineering interesting to you?
Yeah, well, I think I could change because I screwed this second.
No. You must trust that when you do it again in university, it will be easier.
Just as we thought in school.
Yeah. No, but I mean, it's always easier the second time you do it.
Yeah.
Yeah. Right? Yeah. No, don't let your experience with the mechanics, don't let the bad experience deny you what you want to do. No, you don't want to do that, trust me. No. If you go to business, look, Chow came from business, okay? He can tell you don't want to go to business, right? You used to be in business. No, you used to be in science.
I was in business.
You were in business? Yeah.
I have no idea they changed me to the engineer.
Wait. Do you want to be in business or be an engineer?
I have no idea.
All right. Okay.
They just tell me, okay, so you're looking for psychology. So sometimes psychology have two parts. One is business psychology and science psychology. Which one do you want to do? I said I just want to do psychology. Okay, go engineering. That's you can have good experience for you to do psychology.
Well, the reason is, if you do engineering, you can study psychology or science,
IT or
yeah.
both
But if you
sides.
do business, you can't study science or engineering psychology. You can only do one type. So by doing engineering, see, because you said I don't know, then you have to do engineering because you have to keep the possibilities available.
Okay.
Do you know what I mean?
Science is better because of biology.
No, the universities don't care. Like if you want to do psychology, it can be from science or engineering. You know, the only science course that cares that you do biology is maybe medicine. But in fact, I don't even think that they care that much, because they actually only care that you do chemistry and maths for medicine. So, but of course, if you do business and economics, you could never do science anywhere. You know. So when students are unsure of what they want to do, it's better that they do science or engineering. And you probably don't want to do biology because there's too much English and too much boring as well. Yes. Okay. Have we got time to do another one? Not really. So we have a double class on Monday. We will finish Hooke's Law and maybe, so we'll finish materials on Monday and we'll start electricity on Tuesday. Now, how many weeks do we have left? After this week? 4 weeks after this. So how big is electricity? I think it's about 2.5 weeks. Okay, so we'll have 1 week of revision at the end. Yeah. And I think your exam is after Christmas, I think, is it? Yeah, I think so.
For English, right?
Except for English, which is before. Yeah. Yeah, okay, that sounds alright.
Hey, George?